Okay, when we are adding and subtracting exponents, we need to start with what an exponent is. So, as you've already learned, that little number up in the corner is what we call an exponent. In this case, I've written 2 to the second power, or 2 squared, which means we take the number 2 and we multiply it by itself, so that there's a total of 2 2's. Or 2 to the 5th power would be 2 times 2 times 2 times 2 times 2. Now when we're adding exponents, if we have a base that's a number that we know, like 2, and we're going to add a 2 squared to 2 squared. Okay. There's 2 ways to think about this. One way is that we can evaluate the number. So 2 squared is 2 times 2, which is 4. Okay, we can write that up here as well. 4 plus 4. Which is 8. Or, second way, is we can think about this object, 2 squared, as a type of object. And maybe to show that it's one single type of object, I'll put a square around both of them, or a rectangle. Since these are both in a rectangle, the same type of object, okay, they're both 2 squared. And what I see here is that I have 2 squareds. So I have 2 boxes. And inside each of those boxes is a 2 squared. Then I can start evaluating. Okay, in between these boxes is a little hidden multiplication. Okay, and I can evaluate what's inside the box first. 2 times whatever 2 squared is, which in this case is 4, which is 8. This is also a way to say 2 times 4. 2 times 4 stands 4 plus 4. So either way, we get to the same answer. But this way only works when we can evaluate, because we know the base. We have a number on the bottom, 2. But what happens if instead we have 2 to the 5th power times plus 2 squared? So let's say we get this. There's 2 to the 5th plus 2 to the 2nd. Well, now these are ultimately different objects. Okay, I can evaluate both of them because I know how to expand them. 2 to the 5th is 2 times 2 times 2 times 2 times 2, which is ultimately 32. And 2 squared is 4, so we get 36. But that's only because I know the base. I know that it's 2 to the 5th. Okay, but we want to build up a sense of what happens when that's not a number we know. What if it's an x? So instead what I'm going to think about is that 2 to the 5th is a different type of object than 2 squared. They stand for 2 different numbers. And if I can't evaluate them, I have to find a different way to add them together. And in fact, there's not. So there's no way to simplify this, is what I would say. 2 to the 5th plus 2 squared is 2 to the 5th plus 2 squared. That's it. Okay. This is a circle object, perhaps, and this is a square. And so I can't add a circle and a square together in any meaningful way. It's not like this where I say, oh, I have 2 squares, so I have 2 to the seconds. I have a 2 to the 5th and I have a 2 to the 2nd. Now I can evaluate it because I know their value, but I can't simplify it in any meaningful way. Now, what do I mean? Well, if we have an object that's not a number, so let's say we have x squared plus x squared. Well, x is an unknown. X is a mystery number. Whatever it is, we know that we're taking it times itself. X times x plus x times x, but we're not sure what it is, so I can't get to a final number yet until I replace that with something. All I can do is this word simplify the expression. We want to write it with as few terms as possible. Well, if I think about it, again, this is one type of object. This group here, this is a group. I have a group of x squared, and I have another group of x squared. And so what I have is 2 groups of x times x. That's what multiplication is. 2 times x times x. Now the x times x I can re-simplify back to the x squared. 2 times x squared. And that's exactly what the addition is saying. I have 1x squared and I have another 1x squared. And sometimes I like to imagine that I have a little basket and I have some x squared sitting in there. And the question that addition is asking is, how many x squareds total are there in this basket? Well, there's 2 of them. My basket has 2 x squareds. And that's the same thing for any repeated object. X plus x plus x plus x. If we imagine our basket, well, x plus x plus x plus x are all the same object. So how many x's are in my basket? Well, I can just count. 1, 2, 3, 4 x's. Or I can think of each x as a group of a certain type. This is a group of x. Whatever that is, group of x, a group of x, a group of x. And so there's 4 x's in my basket, or there's 4 groups of x, which we just write, 4x. Now take a minute to think about that, right? When we're adding or subtracting, we're thinking about a total number of things. Well, this is the thing. The x squared is the thing that I'm counting. Now what's different is, what if the objects don't match? And we have x to the 5th plus x squared. Well, since I don't know what x is, I can't just give an answer. And so I'm looking again to simplify the expression and write it in as few terms as possible. Well, x to the 5th is 5 x's multiplied together. And x squared is 2 x's multiplied together. But now these are different objects, right? There's 5x's being multiplied here and only 2 here. So I can no longer just count. If I draw my basket again, okay, and I have an x to the 5th and an x squared sitting in there. Well, I can't simplify that in any way. I can't just say, oh, I have 2 of something or 5 of something or however many may be, because these are different objects. It's like having an apple and an orange. We can't say, oh, there's 2 oranges or there's 2 apples. We just have to continue to say there's an apple and there's an orange. So the language around math is related to our English language. X to the 5th power is a different object than an x to the squared. So in fact, I can't simplify this. It's just x to the 5th plus x squared. And that doesn't change no matter what objects we have if they're different. 2x plus 3x plus 4x squared. Okay, this is where we start talking about this idea of combining like terms. Like terms are similar objects, the objects I can just count. Okay, if there's 2 x's in my basket and 3 x's in my basket, well, that's a total of 5 x's. And then also in my basket, there was this other object, x squared, and I have 4 of them. Okay. And in this case, this would be like apples, apples, oranges. 2 apples plus 3 apples, well, that's 5 apples, but 4 oranges, I can't combine in my language. It's just 5 apples and 4 oranges. And that's really what's going on when we are adding exponents. Okay. So I would suggest you try a couple and really think about what's going on here when we're adding exponents. So it could be anything. 2x to the 5th plus 3x to the 1/2 power plus 1x to the 5th plus 2x to the 1/2 power. Pause the video, give it a shot. And if you did what you're supposed to and actually pause it and try it, you should be coming back. And the answer is, well, what are my like objects? The x to the 5th. Okay, let's say that's like my apples or my squares. It's a type of object. And if I have 2 and 1 of them, that's a total of 3x to the 5th. On the other hand, I have this other object over here. Maybe it's my oranges. Or maybe I circle them to indicate that the fact that the exponent is different means it's a different object. And so what I have here is if I have 3x to the 1/2 power and 2x to the 1/2 power, that's a total of 5x to the 1/2 powers in my basket. It doesn't matter what x to the 1/2 power is once we replace x with a number. Well, all I know is that I have 5 of them. Okay. Now, it's a very similar concept for if we have subtracting, right? So let's say I have something like x to the 3x squared minus x squared. Well, again, if we think about a basket, okay, I can't evaluate this, but I can simplify it. In my basket, there's 3x squared. What happens if I take away one of them? How many is left? Okay, that's ultimately what subtraction is always asking us. Or perhaps we could think about it as distance, but in this case, we want to think about how many's left, right? So if I had 3x squared and I took away an x squared, well, that leaves me with 2x squared, right? So there's two ideas happening here. I have 3 of my object, and I'm taking away 1 of my object. One of whatever the object is. And what that object is an x squared. Okay. Obviously, 3 minus 1 evaluates 2. Okay. And we can even start showing the distributive property here. This direction is kind of like undistributing. I'm taking out the fact that x squared is the object they share in common. And what I'm doing, in fact, is actually just working with the coefficients. 3 minus 1. Okay. Let's take another example. It could be any type of exponent. 6x to the 1/3 power minus 1.5 x to the 1/3 power. Okay. Now, it doesn't ultimately matter what 1/3 of a power is. If you have not worked with fractional exponents yet, all that matters is that I know that that's a specific type of object. Whatever x to the 1/3 power represents, it's an object. And I have 2 x to the 1/3 powers. One object here and one object here. Now, if my basket had 6 of whatever that is, x to the 1/3 powers, and I'm taking away 1.5 of them, how many does that leave me with? How many of those x to the 1/3 powers? Well, 6 minus 1.5, you should be able to recognize very quickly, is 4.5. 4.5 what? Well, 4.5 x to the 1/3 powers. I don't know what this number is yet until I pick a value for x, but what I know is that I have 4.5 of them left. Now, again, if I fall into a situation where I'm left with an expression that has something like this, and maybe I'm asked to simplify if possible, well, I can't. There's no simplification that can happen here because these are different objects. And when you're working with exponent, do whatever it takes to remind yourself that these are different. So maybe in my case, I can underline this one with a green and this one with an orange. Okay. X to the 7th is like my apples and x to the cube is like my oranges. They're different objects. Okay, they represent a different number. And if I don't know what that number is, I cannot just count them. So this is as simplified as it gets. In my basket, there's just 4x to the 7th. And I'm taking away 3x to the 3rds. And I can't go any further until I know what x is and I can plug in and start evaluating. And so the summary of how to add and subtract exponents would come to this. Plus or subtract exponents. How do we do it? Well, there's some key points. The base must be the same. What do we mean? Remember, the base is that bottom number. The base is the number that you're multiplying. How many of those things you have. Okay, so in our case of x, in order to be able to add or subtract, the base has to be the same, and this is the base. Why did I say that? Edit. Excuse me. Not the base. I was moving ahead of myself. The exponent must be the same. Okay. The exponent is what determines the type of object you're working with. Okay, if you're squaring something, I can only add that same number to itself if I don't know what it is. You know, my mystery object here has to be the same number in order to meaningfully simplify and just say that there's two of them. Right? Otherwise, I can't add them together. So this is yes, we can do this. But I cannot do x cubed plus x squared. I cannot simplify this. If I replace x with a number like 2, these end up being two different values. Okay. 2 squared plus 2 cubed. Okay, 2 squared and 2 cubed are not the same number. And so if I'm not sure what my mystery number is, it's x squared, it's some unknown number squared and some unknown number cubed, I can't simplify at this point because they're not the same. So I'm no longer simply counting the type of object I have. So this is done. That's as simplified as it gets. Okay, so no, I can't add or subtract if they have different exponents. So if you've got some work you're working on, exponents, try it. Okay?